So the next talk is about climate change. And when I read this, I asked myself, so why do we need to know about this? So we are computer hackers. You know, it's always cozy and warm next to a big mainframe. We don't go outside. So what about the climate? But then I read something that each Google query produces 8.6 gram of CO2 of carbon dioxide. 20 Google queries would make for a kilometer with a modern car. So somehow we're connected with the climate, with the atmosphere. And lately there were lots of information, disinformation about global warming and the great global warming swindle I read somewhere. And now we have the opportunity to listen to Stefan Rahmstorf to get some first-hand information of the global climate research. And Stefan Rahmstorf is member of the I have to spell it right, Intergovernmental Panel on Climate Change. So some of you might have heard about this, and there's a very famous report. He was one of the head authors of that, and I'm looking forward to have a very, very interesting talk right now. So please give a warm welcome to Stefan Rahmstorf.
Yeah, thank you very much. I'm working at the Potsdam Institute for Climate Impact Research. I might add to this nice introduction. Thanks, by the way. Potsdam is just outside Berlin, as hopefully most of you will know, about 30 kilometers from here. And I'm not really a member of the Intergovernmental Panel on Climate Change. I'm just one of the scientists who has contributed to the last report, because this, the IPCC doesn't have real members as such. It has a small head office in Geneva, but mostly it's a voluntary initiative where thousands of scientists around the world contribute in one form or another to these reports. Just that as a point of clarification. My job today is to try and give you a current overview about what we know about climate change. And I will start with the very basic fact that the climate of our planet, at least as far as the global temperature is concerned, is a result of a very simple energy balance, and that actually applies to any planet. So with this you can calculate the average temperature of all the planets in the solar system. You might have recognized the sun on the top left there, and the energy that comes from the sun is of course what drives the whole climate system. And then a part of it, about 30%, gets reflected back into space, mostly by the bright surfaces, that is the cloud surfaces or snow and ice surfaces. And the Earth itself radiates energy in the long wave band like any physical body. It's called the back radiation or infrared radiation. And the global mean temperature simply adjusts so that this equation that you see at the bottom left there is satisfied, namely we radiate as much energy back out into space as we absorb from the sun. And this is an equilibrium, of course, but it holds to a very good accuracy. We can't be out of equilibrium for any substantial time. So that also means that there is only very few ways to change the global mean temperature. Either you have to change the incoming solar radiation, or you have to change the second term here, the reflectivity of the Earth, that's called the albedo. Or the third way is to change the outgoing long-wave radiation, and that's what you can do, for example, by changing the composition of the atmosphere, the amount of greenhouse gases in the atmosphere, because the atmosphere is not transparent for long-wave radiation because it contains gases like water vapor, carbon dioxide, and some others that are called greenhouse gases, and that interfere with this back radiation into space. So there are many things about climate that are very complicated, but this is actually something that's very simple, the energy budget that determines the global mean temperature. That's why we understand global mean temperature much better than any other aspect of climate, like regional temperatures or precipitation and so on. But I will talk about those as well. But I will start just talking about global temperatures. I will also start by taking a look back in time. This is the last 400,000 years. Sorry that the labels here are so small. I have a version of this with bigger labels, and I overlooked that I got the wrong version here. But anyway, this shows 400,000 years of climate change, and the blue curve is the up and down of the carbon dioxide concentration in the atmosphere as measured from ice cores from Antarctica, and the red curve here is the temperature in Antarctica from those ice cores. Many of you will probably recognize this because this is the point where Al Gore in his movie climbs on a ladder and he makes a slight mistake there. We have criticized that on our weblog, Real Climate. Otherwise it's a pretty good movie, but this story he doesn't get quite right. So what I want to tell you about this data is mainly two things. The first of them is that the CO2 concentration has varied between 190 and 290 parts per million for at least the past 400,000 years, as we see on this graph, but we now have a newer ice core, a European drilled ice core, the Epica core, which takes that back about 800,000 years, and it just continues on basically in the same way. CO2 nicely stays within those bounds of 190 and 290 parts per million. And that brings into perspective what has happened recently in the last 150 years or so, namely this increase of the carbon dioxide concentration to, by now, more than 380 parts per million, so it's an increase by about 1/3. And you have to go back several million years in climate history until you come to past climates where CO2 concentration was as high as it is today. And at those times, temperatures were also much higher than they are today. Oops. Can we get rid of this sound, perhaps? Is that possible? Oops. So or do I have to stand somewhere else to avoid this? Well, don't know. The second reason why I show this is because we use these past temperature variations to test the models that we have that we use to simulate climate on Earth. So what we see here is basically 4 glacial cycles. This is the first one, the second one, the third one, and the fourth one. And these glacial cycles are driven by changes in the Earth orbit. That's why I have this little schematic diagram up here, which shows those orbital changes. And these drive the ice ages. I hope that everyone knows that. I learned that in school in the early 70s, because this has been known since the 1920s, basically, the orbital theory of the ice ages, and it's been well confirmed since about the 1950s. And we can use this now to drive our climate models, first of all with these orbital cycles, which are known to great precision. You can calculate this from astronomy, basically. And the second thing we use is this variation in carbon dioxide concentration, which we know from the ice cores. And if we drive a climate model with these two driving forces, these two forcings as we call them, then we can simulate past climate variations. And this movie shows you the last 200,000 years of climate. Time is running at the bottom here. We're about 150,000 years before present now at this point. And what you see here is the big ice sheets covering the northern hemisphere. Now they're vanishing. Only Greenland is ice covered. There was the Eemian interglacial, and we're now gradually moving into the next ice age. Again, that's the last ice age that reached its maximum extent about 20,000 years before present. And now we're about 40,000 before present, so you can see we're gradually approaching this maximum extent that was just there now, and then the ice relatively rapidly vanished again into the Holocene, which is the warm interglacial that we live in today and that we have lived in for the past 10,000 years. That was a time when humans invented agriculture and developed their civilization. The reason why I show this is, first of all, because I think it puts the past, the current climate changes into a longer term perspective, and secondly, I think it's a nice success that we can model these things now with our climate models, the same model that we also use to do projections of the future, or other times in the Earth history we simulate with the same climate model. Let's get closer to the present now, though. This is the last 10,000 years, and again I show you the CO2 concentration, so it's just a part of the same thing that I showed earlier. This is the Holocene, pretty stable carbon dioxide concentration around about 280 parts per million, and then here you very clearly see that strong increase that has happened since. And we know for sure that this increase in carbon dioxide concentration has been caused by us, by human activities. The reason why we know that are manifold, but the most simple reason is that we simply know how much we have emitted. We know how much coal, oil and gas we have dug out of the earth and burnt, and CO2 is simply the main combustion product, so we know how much CO2 we have emitted, and this rise that we observe in the atmosphere is actually only about half of what we have emitted. So there is no question that perhaps this CO2 might have come out of the natural Earth system. To the contrary, we know the natural Earth system has taken up CO2, about half of what we have emitted. There are other reasons why we know this rise is caused by humans. One more technical reason is that the isotope composition of fossil carbon is different from the carbon that naturally cycles in the ocean, in the biosphere and in the atmosphere, and that was already shown in the 1950s that this rise is due to fossil carbon because of its isotope composition. I just said that about half of the CO2 that we put into the atmosphere is not there anymore. It's gone. So where is it? Most of that is in the ocean. The oceans have also increased in CO2 concentration. That is proven by shipboard measurements. And this is a problem in itself because carbon dioxide in the ocean forms carbonic acid, and that makes the ocean more acidic. And that's a problem because it interferes with all the organisms in the sea that form calcium carbonate shells, like this microplankton that you see here, or the coral reefs. They are all made of calcium carbonate, and you can only do that if you have enough calcium carbonate in the seawater, if it's supersaturated. And by adding more CO2 you shift the chemical balance so that you get into a state of undersaturated calcium carbonate. We'll get there in about 50 years if we don't stop the rise in CO2 concentration and CO2 emissions, and then we will see major impacts on marine life. For example, colleagues in Bremerhaven have grown this microplankton in seawater enriched with carbon dioxide, and you see that you then get very malformed shells, etc. It's just not viable anymore to form these shells. It's the same as the seashells that you find on the beach. You can't do that if the ocean water becomes too acidic, and then these organisms are at the basis of the food chains in the ocean. So we are really playing with the entire ocean ecosystem here in a major way. To me, as an ocean scientist, this would be alone enough reason to stop increasing the CO2 concentration in the atmosphere, even if CO2 didn't cause climate change. But we know that apart from ocean acidification, it does also cause climate change, because carbon dioxide is a greenhouse gas which interferes with the long-wave radiation that is radiated from the Earth into space. And that is not terribly new. That's been known since the 19th century, actually since the early 19th century. But the effect was first quantified in the late 19th century in this famous paper by the Swedish Nobel Prize winner Svante Arrhenius, who calculated the effect of a doubling of CO2 concentration in the atmosphere in the year 1896. And his result was that you get a global warming of 4 to 6 degrees centigrade if you double the CO2 concentration. That was actually an afterthought by Arrhenius. He wasn't really interested in doubling of CO2. He was actually interested in explaining the ice ages. And so he first calculated what do you get if you halve the CO2 concentration in the atmosphere, and how much cooling do you get, because he wanted to see whether this could be part of the explanation of the ice ages, which indeed it is. It is a feedback that without that the ice ages wouldn't be so cold, and you can use that to determine how sensitive the climate is to CO2. This effect of a CO2 doubling is called the climate sensitivity because it does tell you how sensitive the global temperature is to a change in the CO2 concentration. And the modern estimate for this is 3 degrees. Rather than the 4 to 6 that Arrhenius got, but you have to you have to grant him that he didn't have a computer, and he had to do it all with pencil and paper, and also, more importantly, he didn't have access to all those data that we have now that tell us about the strength of the feedbacks in the climate system, the water vapor feedback, the cloud feedback. He had only rough estimates of these, so his number of 4 to 6 degrees is not far off what we today think is a real number, namely 3 degrees with a remaining uncertainty of plus minus 1 degree, which is mostly due to the cloud feedback, which is still not well enough understood to narrow down this uncertainty. But there are many independent ways of determining this climate sensitivity, including from the sophisticated computer models of climate, but also from data from the Earth history. This is what has been done in my group, for example. And all these different studies, there are 13 different estimates of this climate sensitivity listed in the latest IPCC report. They all come consistently to the result that it's around about 3 degrees. So if you double the CO2 concentration, you heat the planet by 3 degrees. That immediately allows you to calculate how much warming should we have caused by now, by that increase in CO2 that I showed you. And it's slightly more complicated because you have to take the other greenhouse gases into account as well, not just CO2. And you also have to take into account the thermal inertia of the oceans, which means that we don't immediately get the full warming, but rather we lag behind, always by a few decades, behind the full-blown warming that we will get eventually from that rise in greenhouse gas concentration in the atmosphere. But this is relatively easy to calculate on the back of an envelope, and with 3 degrees climate sensitivity, the changes in the atmosphere that we have caused up to today should have caused a warming between 0.7 and 0.9 degrees centigrade. And you can compare this is the forecast of physics, so to speak, of that global energy balance equation. You can compare that to what really has happened, and this is what the data show. They indeed show a global warming of 0.8 degrees over the last 100 years or so. And the thick line, by the way, is a trend smoothed over 15 years, and the individual dots here are individual years of the global temperature. And you can see that apart from the long-term trend, of course, there is a wiggly up and down. That's just weather. That's natural variability that you get from year to year. And 2008 happens to be a relatively cold year, which is way below the trend line. The previous years have all been above the trend line, but that's simply natural variability. I stress that because there are some people who try and read all kinds of things into this relatively cool value, but you can see here that many times in the past you get individual years that are way below the long-term trend, as you get some that are way above, like this one or 1998 here. That is just the natural variability, and you have to take the trend over a long time, like 20-year time span or so, to get a robust statistical estimate of what the trend is. And it is pointing up at a rate of about 0.17 degrees centigrade per decade. The ocean temperatures go through a similar warming, by the way, so it's not some kind of urban heat island problems with the data or so. That's also shown, for example, by the glaciers vanishing in the mountains. Clearly, glacier melt can't be caused by urban heat island. I should perhaps say why we have this funny shape of this curve. This is due to the fact that, of course, CO2 is not the only factor that influences climate, but we have the observed climate as a result of all the combined effects, like including natural variations like solar activity changes, as well as all the human-caused climate impacts, that is not only the CO2 but other greenhouse gases, but also cooling effects by air pollution, so-called aerosols, which offset some of the greenhouse warming that we're causing. And if you look at this curve, in the first, you see three phases. The first warming phase here is a phase where you have solar activity increasing as well as greenhouse gases increasing, and both of them have contributed to this early warming up until the 1940s. Then you get this plateau phase. Here solar activity stopped increasing and actually has shown a slightly downward trend since the 1950s, and you get a big increase in aerosol pollution during this time, which led to the famous or infamous London smog, for example. Many thousands of people died from that smog until power stations were fitted with filters and the air pollution was cleaned up. And so in this phase we have basically rise in greenhouse gas concentration, but also rise in the cooling effect of that smog, and they roughly balance each other. And then the smog pollution was reduced, greenhouse gases keep increasing, and solar activity is pretty flat, slightly downward during this time, but it's too weak to offset much of that greenhouse caused warming. I put some historic dates on here. This is when Arrhenius first calculated the effect of CO2 doubling, purely academic exercise at the time. Actually, they thought it was a good thing. There were articles written, we should emit more CO2 by burning open coal mines, so that we get a nicer, warmer climate. That's what Arrhenius said. Maybe it has something to do with him coming from Sweden. He obviously didn't think through the consequences very well, sea level rise, etc., which I'll come to in a few minutes. Now, the first specific time forecast was actually made in the early 1970s by a famous British meteorologist, John Sawyer, who published in Nature an article in 1972 saying that because of the observed rise in greenhouse gas concentration, there should be a warming of about 0.5 degrees centigrade by the end of the century. And it's quite remarkable that he made this forecast at this time here, when there was no sign of any actual global warming for the past decades, quite apart from the fact that this data set, the globally compiled reliable data sets, were not available at the time. So people didn't actually know what the global temperature was doing when he made this forecast. But he turned out to be pretty right, because by the year 2000 there was indeed about 0.5 degrees centigrade of warming. In the late 1970s, the first time a major scientific organization, namely the National Academy of Sciences of the United States, warned of the impending global warming due to carbon dioxide increase. And then in the 1980s, the IPCC was founded, and in 1990 issued its first report that was here. And by now we are into the fourth IPCC report that was published last year. If we didn't have those data, we would still know that climate is warming. I mentioned it. The glaciers in the mountains are vanishing almost everywhere on the planet, with very few exceptions where snowfall rates have increased. This is a picture from the southern hemisphere. I took that in New Zealand, of the Muller Glacier, and you see where the terminal moraine of this glacier is, where it was 100 years ago, and it's basically collapsed into a puddle, little meltwater lake that has formed here, and you will find this picture all over the world. You can also see the warming from space. So if any aliens from space are observing us. They know exactly what's going on. They just have to look at the ice cap on the North Pole. This shows the sea ice cover in the polar ocean from satellite data. This picture is 1979, when we first had the satellite up, and this is 2007. So if you compare those two, you can see how much the Arctic ice cover has shrunk. And this year, in 2008, for the first time in living memory, we had the Northwest Passage through here and the Northeast Passage through here, both ice-free, so ships could simply go through there, and a German research vessel circumnavigated the whole North Pole without any problem having to break through ice. This is a time series that goes with that, and you see the steady decline of sea ice cover, and then a strong minimum in 2007, and the 2008 value wasn't much higher than that. So there is some legitimate concern that this trend is not just going to continue linearly, but it's actually accelerating, and we might see a relatively rapid end of that sea ice cover in the summer in the Arctic Ocean over the coming decade or two. This decline, by the way, is faster than predicted by any of the climate models. I mentioned that there are things that are simple to calculate, like global mean temperature, but there are things that are much more complex, like the behavior of ice, and obviously our models are not doing a very good job here, and unfortunately they have been underestimating the problem. So let's look at the future. If we accept that the climate sensitivity is about 3 degrees warming for a doubling of CO2, then you can easily calculate how much warming we expect in the future, and it mainly depends on how much greenhouse gases we will emit. And that's why there's different scenarios. They have names like A2, B1, etc. They are just different emission scenarios, so that means different assumptions about how our economy will evolve and how much in terms of greenhouse gases we will emit. In a way, these are not a forecast, and they're not called forecasts, they are scenarios, because we have a choice which one we want to get on here, because it is still in our hand how much greenhouse gas we will emit in the future. But plausible scenarios give us a warming of 3, 4, some even go up to 6 degrees warming this century, the more extreme scenarios. This, by the way, is not an emission scenario. This is called commitment, and that is if you simply from tomorrow, or actually not from tomorrow, from the year 2000, so it's already in the past, froze the amount of greenhouse gases in the atmosphere and kept them constant ever after. That just shows you how much extra warming you will still get simply from the inertia in the system, even if you had stopped the increase of greenhouse gases completely. So there's some limited amount, a few tenths of a degree of warming that are basically inevitable anyway by now. That's just the global mean temperature, and that's not telling you the full story, because there are big regional variations, which you see on this movie. This is the highest resolution climate model run by the Japanese colleagues on a major supercomputer called the Earth Simulator, which for quite a long time was the fastest supercomputer on the planet, but by now it's already been overtaken by other computers. This is the year here. Nothing too much exciting to be seen yet. You start to see the warming in the Arctic quite clearly now in this computer simulation, as it has indeed happened in the real world. But as we go further into the 21st century, you start to see some real hotspots of warming. Himalayas, for example, here. These are the regions where the snow and ice cover shrinks, and that's why you absorb more radiation from the sun and you get extra amplified heating. This is getting quite uncomfortable now towards the end of the 21st century. This scenario actually is a global mean warming of 4 degrees, so it's not extreme, it's a kind of middle of the road greenhouse gas scenario, but 4 degrees global average warming means more than 6 degrees in most continental areas. That's simply because 2/3 of the planet is covered by oceans, and the oceans have a big thermal inertia. They don't warm up as much as the continents, so don't get deceived by those global mean numbers. The global mean is made up mostly of the ocean that stays quite cool. Where we live on land, you get a lot more warming, and especially in the high latitudes in the Arctic, you have warming in excess of 12 degrees now in this scenario, simply because the ice is vanishing, and so the Arctic heats up due to the ice albedo feedback effect. Now let's talk about some of the consequences. The consequences are not mostly the changes in the annual average global mean temperature, or not even the annual average local temperature anywhere. The most effect of climate change are actually in the extremes and in other things like the water cycle, etc. The first of these impacts of climate change is the frequency of heat waves. I think to any layperson it's plausible that you get more frequent heat waves as the climate gets warmer. And an example of an extreme heat wave we had in Europe in summer of 2003, which caused at least 35,000 fatalities, and it was the greatest natural disaster in the past centuries in Europe. This, of course, for one individual event, you can never tell whether it's caused by global warming or not, because this is a statistical game. It's like having loaded dice, and if you throw 1/6 with a loaded dice, you don't know whether this one would have come anyway, or whether this is because the dice was loaded. So all you can say scientifically is that the frequency of such events increases. You can't say whether any individual event can be attributed to global warming. That's the same with Hurricane Katrina, for example. I come back to tropical storms, but you can never attribute a single event to global warming, because there is too much simple chance in the climate system. This chance is simply weather, which has nothing to do with the long-term trends. So let's look at the longer-term time evolution then. The black curve shows the observed values, that is the summer temperatures in Europe, and you see since the year 1900 you see a shape of the curve very similar to the global mean temperature, also here for the European summer temperatures, and you can see that the summer of 2003 was an extreme outlier. It was quite unexpected. I was shocked when the numbers came in of those extreme summer temperatures there, because it was outside that natural variability range that you expect, and it's still not fully explained what happened there. There must have been some nonlinear feedbacks acting. But I want to point you to this model simulation by the British colleagues from the Hadley Centre. This is the red curve, and that's what their climate model does, and it reproduces the past very well, as you can see. Of course, not individual years, because individual years, remember, that's just weather, that's random chance. What a climate model is supposed to do is not predict whether any individual year is warm or cold, but it should reproduce that spread of natural variability, and it should reproduce that long-term trend, and the model does that quite well. You can also see that in the climate model you don't get a hot summer like 2003 anywhere near here. You get the first one that is as hot as that in about 2020 or so. But by the 2040s, a summer like 2003 is just normal, and by the 2060s you hardly ever get such a cold summer anymore. This just gives you a feeling how the extreme temperatures shift when the background climate gradually changes. Now another aspect is the precipitation. Precipitation is even harder to predict than temperatures, even regional temperatures, and in some parts of the world the models contradict, because some show increase, some show decrease in precipitation. But one region where all the models agree that we get a strong decrease in precipitation due to the CO2 warming effect, it's the Mediterranean region. This inset here, that's the model simulation for the end of this century, and it shows a strong drying out of the whole Mediterranean area, Spain, Portugal, Greece, Italy. And on the left, the bigger panel here, this is actually the observed trend over the past 40 years or so. And it shows that what the models predict due to the CO2 effect is already happening. We already observe drying out of the Mediterranean countries here. And one of the consequences of this increasing drought problem in this region is fires, because the drier it gets, the harder it gets to fight fires. They get out of control, and we had one of the major forest fire disasters last year in Greece, where the historic site of Olympia almost burned down. It was just rescued at the last minute. By the way, I know there are probably some guests from the United States here. The same applies to California. California is another region in the subtropics where all the models say we expect a drying out of California. The data show California is actually drying out, and you get major forest fire problems happening in California in recent years. Another impact of climate change, that is simple physics, is sea level rise. If you warm the climate, sea level will rise for two reasons. Firstly, warmer water expands, it takes up more space. So that's the thermal expansion component. And secondly, you melt ice that is sitting on land, mountain glaciers and the big ice sheets in Greenland and Antarctica. So additional water flows into the sea. And indeed, sea level is rising. That's what these measurements show. Has risen by about 20 centimeters since the year 1880. And this is also a modern phenomenon. You will sometimes see this disinformation floating around that says, well, this has kind of been going on for thousands of years since the end of the last ice age or something like that. That is nonsense. The geological data show that sea level after the last ice age reached a high stand several thousand years ago and has very slowly been dropping since globally. And also, you know, if this had been going on for thousands of years, 20 centimeters a century, in Roman times, sea level would have been 4 meters lower than now, and you wouldn't understand where the Romans built their harbor walls, etc. They would have been high and dry. And we know from Asterix that they were quite stupid, those Romans, but they were not that stupid. So I actually study climate and Earth history. That's what my research group mostly does, paleoclimate, and that's also what I contributed to the IPCC report. It has a whole chapter on paleoclimate. That's natural climate changes going back millions of years, and they give us a clear warning. You can plot here how past climate change have affected sea level, and this is today. That is, we have a global temperature of about 15 degrees centigrade today, and sea level is here shown on the vertical axis relative to today. That's why today is marked 0 here. Now, if we go back to the last ice age, where I showed you this computer animation movie in the beginning, it wasn't only about 5 or 6 degrees colder in the last ice age, but sea level was 120 meters lower. That's all this big ice that you saw on the continents. That's enough ice to lower global sea level by 120 meters. So that's this point here. If you go back further in time, you come to times with warmer climates. The last time that was the case was the Pliocene 3 million years ago. Was about 2 to 3 degrees warmer then globally, but sea level was about 25 meters higher. And if you go back even further, 40 million years ago, that was the last time the planet was ice-free because it was so warm. And that was only about 4 degrees warmer than now, but sea level was about 70 meters higher because of all the ice having melted. And so you see those fall almost on a line, those points. That's what the Earth history is telling us. Now, the forecast by the IPCC for the year 2100 is about 3 degrees warming, but less than 1 meter sea level rise. And the reason why that is so low, compared to the experience of the past, is that sea level responds very slowly. At least we hope so. So that in the beginning, in this century, we will only see a tiny beginning of a much bigger sea level rise problem that will go on for hundreds and thousands of years after we have stabilized the global temperature again. And that long-term big sea level rise mostly comes from the big ice sheets. Here's the Greenland ice sheet. That alone has enough ice to raise sea level by 7 meters globally. And the glaciologists are telling us if the global temperature increases by 2 or 3 degrees, very likely the whole Greenland ice sheet will go. The only question we can't answer is how fast can it go, but people increasingly think, and I quote Jim Henson here on that, the head of the NASA Climate Institute, that this might only take centuries and not millennia as we have previously thought. We fear that now because the ice is showing dynamic changes, it's starting to flow much faster, and that's an aspect we cannot simulate in the ice sheet models yet, at least not very well. So there have been some new sea level estimates published in the last year or two, and I show you a couple here. That the most interesting is this one by the Delta Commission. They did an estimate for the year 2200 and for the year 2100. That is a kind of high-end estimate of the worst thing that could happen, and it was ordered by the Dutch government, and it's used by them to plan their coastal defenses. And they put together a committee of 20 sea level experts from around the world that gave their report to the Dutch government just a couple of months ago. And they estimate by the end of this century between 55 and 110 centimeters, and by the year 2200 between 1.50 meter and 3.50 meter of sea level rise. So this is kind of the longer term where we're heading towards, and that sometimes gets lost in the public discussion because of this focus only on the year 2100. 2100 is too short a time scale to understand what the sea level is doing. It unfolds on much longer time scales.
So how big will the Netherlands be if this really happens?
Okay, how small? I will take some questions at the end, but I will answer this one quickly. The Dutch coastal engineers are confident that they can cope with 3 meters of sea level rise. I'm surprised by that, but Holland does have a pretty straight coastline, and they have a lot of experience. They have a relatively short coastline compared to the number of people that live there, so they can afford very expensive coastal defenses. And those conditions are not true in other parts of the world, like Bangladesh, for example. People are simply too poor, and the coastline is not in a good shape where you could easily defend it. Or example, New York, that I just put up here. This is what a once-in-a-century storm surge does to southern Manhattan. This blue thing is how much it penetrates the street grid of Manhattan. This would be a multi-billion dollar disaster which floods subway stations and things like that. Now today that is statistically once in a century, but after 1 meter sea level rise, this will statistically happen once every 3 years if the storm frequency remains the same. And obviously, you cannot cope with such a disaster every 3 years. You can if it happens once in a century. That's why New York is planning these coastal defenses, storm surge barriers, the red ones here. They're not building them or planning them. This hasn't been decided. They're discussing them. The mayor's office has been debating this. And you see how complicated it is. You have a very complex coastline here in New York. They have about 1,000 miles of coastline because of all these islands. And you have to build already 3 storm surge barriers to protect Manhattan. And you still have lots of Long Island here where JFK airport is, etc., unprotected. You can't really do much there. So many parts of the world, there is no way you can protect yourself against the extra storm surge risk that comes from even 1 meter of sea level rise. Okay, final impact that I want to discuss is the tropical cyclones. This simply shows where they are normally in the last 30 years or so. It's those green areas which are those at risk from tropical cyclones. You see the red dots, they are mega cities, major population centers that are situated right in the track of those tropical cyclones. And climate change has a double impact on these regions. Firstly, sea level rising, of course, increases the storm surge risk from those tropical cyclones, but also some recent analysis increasingly show that the strength of these tropical cyclones is increasing, especially the strength of the strongest ones, the category 4 and 5 hurricanes or tropical cyclones. This is not entirely settled science yet. There is a healthy debate about this, but this year in Nature, the so far, in my view, best analysis has appeared where they reanalyzed the entire global satellite data set since 1980 with a uniform method to have a really homogeneous data set. And they found that 1 degree warming corresponds to about 30% increase in the number of severe tropical storms in the past over the observed values since 1980. And there is a good physical reason for that, because the energy source of those storms is the warm seawater. That's why they only occur in the tropics. Okay, I'll skip that because I want to come to the solutions, and I also want to leave enough time for a discussion. First of all, who causes the problem? That's also interesting to look at this on the individual country basis. Here, this is a distorted map where the size of each country corresponds to its total CO2 emissions over the past 50 years. And that's why the United States is pretty big here. And Africa, for example, is rather small because they have very low CO2 emissions. The colors are the per capita emissions. So the orange and the red countries are those with very high per capita emissions. You see, for example, that countries like India and China, they are big because they have big populations of about 1 billion or more than 1 billion each. But per capita, they're actually quite low in emissions, and that's why, of course, India and China say the industrial nations have to take the lead when it comes to reducing their carbon dioxide emissions. So, what do we need to do to stop the warming trend? We can still stop it, and the goal of the European Union and also the German government is and has been for a number of years to limit global warming to 2 degrees centigrade. That's the magic 2 degree limit that is much discussed, and it looks like more and more countries are also agreeing with this and adopting this, and hopefully now the United States as well under the new president will join in this effort to limit global warming to a maximum of 2 degrees. And that is above the pre-industrial value. So we've already had a warming of 0.8 degrees. That gives us another 1.2 degrees of warming before we can stop it. And there is very little chance to get much below those 2 degrees. You'd have to take really draconian measures to reach that. But with more realistic measures, you can actually just about keep the warming under those 2 degrees. What you need to do for that is you follow these green scenarios. This green band, these are emissions of global greenhouse gas emissions that give you about a 75% chance to stay below that 2 degree limit. So if you follow this green corridor here, you've basically have a very good chance to stay below the 2 degree warming limit. If we do nothing, emissions will continue to increase, and they have actually up till 2008 or so followed very much here along the upper path of those scenarios. So this is what we get when we do nothing, these red curves, and we need to kind of stop the trend of rising emissions, go to falling emissions, and reduce the emissions by at least 50% here by the middle of this century. That's the challenge, but many detailed studies have shown that it's possible to reduce the emissions that much without compromising our economic well-being. And what is needed for that is a major transition in our energy system towards much greater efficiency and towards renewable energies. And I just show you one picture, one possible scheme, how Europe could be supplied with 100% renewable electricity by creating this European supergrid where we network all the different countries so that we can feed in the renewable energy from the best sites all around Europe. For example, wind power from the North Sea area here, and solar power from Spain, but also from North Africa. This is the new thermal solar power station that has been opening in Spain this year. So based on such a scheme, you can also cope with the fluctuations that you always get in the renewable energy supply, wind fluctuations, and that's this problem gets greatly alleviated if you have a large supergrid, because the wind is always blowing somewhere, and you always have somewhere you have solar power, and you can. This has been worked out on an hour-by-hour basis with real observed wind data, etc. And with such a system, you need about 20% energy that you use for regulation, and you can do that with the hydro lakes in Europe and with some amount of biomass which you can store as a renewable energy source. But most of it, 80%, you can do directly from wind and sun. And by the way, the costs have also been worked out, because these kind of power stations, they exist. So you know what they cost to build, and the cost of this system would supply us electricity at about the same price as we have now. It's not more expensive than the fossil system that we have now. It's just a question of we are now locked into an old style infrastructure. How can we get the political transition to a different system against the resistance of those players that benefit from the current system that we have now? I mentioned that economically, there have been many economic studies that show that this is not a big deal. It's not as big a problem as the financial crisis that we have now. And yeah. Let me sum up, because we want to have some time for discussion. Main point is we are in the midst of global warming. The data show that. That's very clear. So far we have seen a warming of 0.8 degrees. And the anthropogenic greenhouse gas emissions are the main cause of this. That's also very clear. And this warming has a series of impacts. Extreme events, heat waves, droughts, flooding, storms, sea level rise. I mentioned those. And if we leave this going on unchecked, so far we've only had 0.8 degree warming, and we already see pretty substantial impacts. If we leave this unchecked and we end up with 3, 4, 5, 6, some scenarios, even 7 degrees global warming by the end of the century, then we will not recognize this planet, I can tell you, and it will not be a pleasant change that we find there. There is a risk of real surprises in the system, because we cannot predict everything, obviously. We can do the global temperature pretty well, but all the impacts, methane release from permafrost or from the seafloor, etc., these are all incalculable risks that we run if we change the climate too much. But we can do something. We can't stop the warming right away, but we can, over the next 50 years, we can stop it if we gradually ramp down our emissions globally by at least 50% by mid-century. In this way we can limit the warming to 2 degrees, which will hopefully make the consequences still manageable, and so that we can adapt to those changes. Thank you very much for your attention. Yes, we have immediately one question here.
I have 2 questions.
Okay.
Number 1, you talked about tropical cyclones. What about tornadoes? Do they increase in number and in strength? And the second question is, what part of the CO2 emissions do IT systems have?
Okay, I can't answer that second part. I don't know. You mentioned how much one Google query causes in emissions. There certainly is, I've heard that the internet already consumes like 10% of the global electricity or something. So there is a lot of scope there also in the IT sector to reduce the emissions by more intelligent technologies. Your first question, tornadoes, as far as I know, there's no evidence that tornadoes have increased in frequency or strength due to global warming.
Okay, in the beginning you showed us the chart with the temperature and the CO2 levels from the ice cores, and they showed that the temperature almost follows the CO2 increase. And then you showed the ice ages, which can be seen in this graph. But then you said that the temperature and the ice ages were explained astronomically by changes in the Earth's circle around the sun. So does the CO2 level also then follow from the sun, or there seem to be two explanations for the same phenomenon?
No, the CO2 indeed varies the variations look very similar to the temperature variations, but if you do a very detailed analysis, you find that CO2 is actually lagging slightly the temperature changes. So what's happening there is that first the orbital changes, they change the temperature, and those temperature changes with a certain time lag also cause changes in the CO2 concentration, which then, because CO2 is a greenhouse gas, amplify the initial temperature change. So it's an amplifying feedback in operation there. And by the way, this feedback explains why the whole Earth experiences ice ages at the same time, which otherwise would be a bit of a mystery, because if you look at these changes in the Earth orbit, when the northern hemisphere gets more sunlight, the southern hemisphere gets less, and so you would expect that the two hemispheres go through ice ages just out of sync, but they don't, because there's this synchronizing effect of the global CO2 concentration, which acts there as a powerful feedback.
I've got a question regarding the solar activity, because it seems that the sun is has an activity of 11 years with the sunspot numbers, but it seems that there are also very long cycles. And in the Middle Age, it seems that there was what they call a Maunder minimum, where the sun activity was very, very low. And it may have an influence on climate. Do you know more about this?
Yeah, sure. The solar activity, first of all, the biggest change that we see is an 11-year cycle, the Schwabe cycle, and that, as you probably know, has no big effect on the global temperature, because, or have you ever heard that there's every 11 years we have particularly warm global temperatures? That's not the case. I mean, the effect is minimal of that 11-year cycle. The longer term changes, this Maunder minimum was a time when you had practically no sunspots and very relatively weak output of the sun. That was only a few tenths of a degree colder than the times earlier or later. So even that really major change where there were no sunspots caused such a little global temperature change that if the same thing were to happen now, there was some speculation whether we might enter a new Maunder minimum, because it took a while for the first sunspots to appear in the last year. That would not slow down global warming in a substantial way. It would be much smaller effect than the effect of rising greenhouse gases that we have now. And you can see, I mean, the last 20 years solar activity has been declining, but it hasn't slowed down global warming. It just continues practically unchanged. Maybe without that you'd have a little bit more global warming, but it's, compared to the anthropogenic greenhouse gases, it's a small effect.
In the end of your talk, in the what can be done, what has to be done section, you mentioned restructuring, rebuilding power supply, and how it could be done even for less money than the financial crisis has already cost, or will cost, as I understood. But you didn't mention traffic systems, which also are big CO2 emittent, and I think it also could be and should be restructured and modified in a big deal. And well, as far as I understood, governments, just as a reaction to this financial and economic crisis, do not have much other ideas than rescuing car industry and building more streets and highways for cars, which doesn't seem an appropriate answer.
Yeah, I can only fully agree with you. I'm a great fan of zero-emission vehicles, namely bicycles. But in addition to that, the combustion engine only has an efficiency of about 20%. So 20% of the energy that you have in the petrol actually goes onto the wheel. If you switch to electric cars, you can get an efficiency of 70 or 80%. And that starts to make sense at the moment where you have this energy system based on renewable electricity from wind power, say, then it becomes very efficient to run electric cars, and you can reduce the emissions by a factor of 2 or 3 by making this system change. So that's another, of course, we have to, in every sector we have to make changes to get the emissions down. There's not one silver bullet or two, there are many changes right through the way how we run our economy and how we live, etc.
Electric trains, tramways.
Trams, yeah, public transport. In Berlin you can see a functioning public transport system where many people don't have a car. I think car ownership is like 50% or so on the number of households in Berlin. And my household, for example, we have 2 small kids. We don't have a car because it's easy to get around, small scale with bike and ride through Berlin with the S-Bahn and trams, etc.
Hello? Yeah. So I'm from the Netherlands, so I'm naturally a bit concerned about global warming. But I do think it's important to realize that the fossil fuels have gave us so much technological advancement, and they even gave us technologies like solar power. So it is our responsibility indeed, but don't you think it's better if you make a strategic decision to end this? I mean, to solve this problem, wouldn't it be better to do that, let's say, 50 years from now, once we've sucked out all the oil and once we have better technology?
Well, it's too late to limit global warming to 2 degrees if we continue on for another 50 years. Actually, even if we continue on and do nothing for another 20 years, it will be too late to still limit global warming to 2 degrees. So we have to turn the tide of rising emissions and go to a path of decreasing emissions within the next 10 to 15 years to still have a chance of making that. And if you let the warming run not to 2 degrees but to 3 degrees, you run a high chance of losing the Greenland ice sheet, for example, with all that sea level rise, etc. So I think, no, we cannot wait. We have to act now.
Don't burn the earth, make plastic toys.
I was just going to say I admire how calm you are saying all this, and I would like to ask how frustrated you are by the results of the latest climate conference in Poznan just a few weeks ago, where many environmental groups have said that nothing really has been changed, or no real change has been started with what's been resolved there.
Yeah, I actually was in Poznan, but only for a day. But yeah, it's frustrating. In a way, it was expected, though, that Poznan would not really make great progress because the situation is in a state of limbo with the US administration changing over. They still had a delegation from, of course, the old US administration there, which still tried to play their game of obstructing progress, etc. And yeah, everybody is really waiting for the Copenhagen conference next year, next December. If that doesn't give a breakthrough, then we're in real trouble.
Isn't it important then to raise awareness, to really...
Isn't it important then to raise awareness and start campaigning now so that Copenhagen shows real results?
Go for it. Yeah.
Talk about positive action tomorrow in the new Lightning Talks section.
You didn't talk about the impact of the heating on the heating system of the planet, because I mean most of our regions are heated by the streams over the oceans. So what is the impact of rise of temperature over the Gulf Stream, for example? Because you have once you have heating, you have more dense salty water, layers of salty water that constitute the Gulf Stream. So that should have an impact on how the planet is heated. And my second question is, in the movie of Al Gore, he shows that some glaciations happen quite quickly, like in a period of 10 years, and, due to some big chunk of ice that goes into the Gulf Stream and blocks the heating system. So I want to know more about this.
Okay, that's actually my main area of research, and I could give a 2-hour lecture on that, but I'm not. I just try and give you the 1-minute answer. The most likely thing during this century is that the North Atlantic Current, which is the extension of the Gulf Stream, will get weaker due to global warming because the Nordic seas get diluted with fresh water from the melting ice, and that makes the water harder to sink down, and so the whole system will likely slow down. There is an up to 10% risk of abrupt changes in those ocean currents. That's what the IPCC report says, but we can't predict those with any confidence. So it's one of those risks of surprises that we still have in the system. And indeed, in the Earth history, there have been very abrupt climate shifts due to shifts in ocean circulation. That's how we know that this is quite unstable, the system. But one thing you got confused, these are not global changes. They are regional to the North Atlantic, because what the ocean currents do, of course, is if you think of that energy balance that I showed, they don't feature there because they only redistribute heat from one place to another. So in the global mean, they have no effect on the global temperature. They have an effect on regional temperatures. I think we have to wrap it up.
I'm very sorry, we have to stop this now. It's a really, really interesting topic. I think maybe you'll stay here for a few minutes afterwards. So
okay,
you might come up here and talk directly. Thank you very much for this talk. I think this is worth a big applause. I think you all should.
Thanks.